So crystals are very highly ordered, but don't really have that much information in them, because just repeating the same amount of information. Now the other thing we have is specified complexity. In the beginning, God created. You see, that's not ordered, there's no repetition there, but it's definitely not random either. In fact, for a program to work this out, you'd have to say you've got a program which says I, then N, then space, then T, so you've got to specify the letters there. And living chemicals, the DNA and the protein, are like the specified complexity. They're not regular and repeating, but they're also clearly not random. Like you've got the, this is a protein called myoglobin. It stores oxygen in the muscles. And therefore, it has to be very highly organized to store an oxygen in the right place, but also releases it at the right time as well. No point storing it if it won't give it back again. So it has to store it and then give it back at the right time. And that requires a lot of organization. It's not just random, it's not just like a crystal with the same pattern repeated over and over. And in fact, John Kendrew was the one who first discovered the structure of myoglobin. He used X-ray diffraction. That's how you normally work out the structures of molecules. And he said, you'll be amazed, just like the world was in 1960, at the beautiful intricacy of this protein. As indeed we should be. What's sad, though, is that a lot of people believe that this intricacy came about by time and chance and natural selection. And to get back to the DNA code, see, even a DNA code, which is to translate from the DNA information into the proteins it's coding for, has amazing amounts of information in it. Like, for instance, a certain sequence of 3 letters of DNA code for 1 protein letter. See, 3 base pairs of DNA code for 1 amino acid in a protein. But from a chemical point of view, some of these amino acids are very similar, very hard to separate from a chemical point of view, but in the human body it makes an enormous difference to get one out of place. Because the enzyme systems in living things are far more sensitive. You need to have things in the right sequence for it to work. And therefore, for one thing, what this is, the molecule is to link the 3 bases which code for isoleucine. So it's linking the bases of isoleucine to the actual amino acid isoleucine. And it's an amazing system here, because what it does is, first of all, you've got lots of different amino acids linked to different bases here. But what this enzyme is doing, it screens out the ones which are too large, first of all. And then it actually has another sieve which screens out the ones which are too small. And it's just the right size that the isoleucine one comes out. Anything bigger is blocked off at one end, and anything smaller is let out the other end. And this is an amazing amount of control. And yet you need this protein for the DNA code to work. If you haven't got this protein, you cannot get the DNA code coding for isoleucine. Because you might find the 3 letters might produce any of these other amino acids instead of just the isoleucine which is required in the protein in this particular place. In fact, there's always another thing to talk about to show you how chance is not enough to produce things, but because I said natural selection won't work, so you have only got chance. And let's see what sort of chance we have. Well, let's make it as generous as possible for the evolutionists here. If they estimate 10 to the power of 80 atoms in the universe, that's 1 followed by 80 zeros. That's the number of atoms in the entire universe. And if you say 1 trillion atomic interactions per second, 10 to the power 12, and 10 to the power 18 seconds in the universe, if you believe the Big Bang is true, which I don't, of course, that's the 15 billion years. Now, that means that there are 10 to the power of 110 interactions possible. That's 1 followed by 110 zeros. That's the total, the maximum number of interaction between atoms that are possible, even if you grant the entire universe was participating, even if you grant that it's as old as the Big Bang as say it is. There are 20 amino acid letters, and if I'm saying there are 256 enzymes for the simplest life, and that's, I think, very doubtful. I think it's going to be far more complicated. I think this is far too simple, as I mentioned before. Now, each of these enzymes is composed of lots of amino acids. Now, there might be some leeway in some of the amino acids, but so there are certain ones which can't be changed because they have to be in that right shape for the reaction to occur. So I'm just being generous to say that only 10 of them have to be exactly right. But when you work it out, you find that there's one chance in 10 to the power of about 3,000 to get the right sequence for life. Now, when you think of you've got a bank card, you've got a PIN, I hate the term PIN number. I mean, it's PIN, isn't it, right? Personal identification number is ridiculous. Okay, so you've got a 4-digit PIN, and you're not supposed to leave it lying around anywhere. You're not supposed to have it written down. And the point is, if someone else steals your card and guesses the right PIN, the bank's going to say that you left it lying around somewhere. Because it's 1 in 10,000 chance, or 3 in 10,000, because you've got 3 goes of getting it right. 3 in 10,000 chance of getting it right, and the bank thinks that's enough protection for you. But here, it's like getting a 3,000-digit PIN number. See, if a 4-digit PIN number is pretty good protection for the ordinary person using a credit card, well, what's a 3,000-digit PIN number like? It's totally impossible. And when I say 10 amino acids must be the same, well, that's incredibly generous because you've got plenty of proteins like calmodulin where 142 out of the 143 amino acids must be exactly right. And to try and get that by time and chance is just amazing. Just that one protein alone, the chance of getting that is about 1 followed by 185 zeros, just for that one protein, which is essential for metabolizing calcium. Now to get back.
Welcome back to Truth Seekers. Phone numbers are up there, so you can give us a call if you'd like with comments or questions. Brandon, that's pretty complex stuff. All those enzymes necessary for life.
Necessary.
That speed things up millions of times.
Trillions of times, yeah.
So you need to have a number of things here, don't you, to get life started?
You do. You need all those enzymes, and he was bringing up a lot of numbers, and it may be confusing to some, but the thing to look at is that there is so much complexity and there's so much necessary for life. That's why it looked complex, is because it is complex. There's so much necessary for life. Toward the end there, he talked about calmodulin and the odds of just getting this one protein right. Well, he suggested there are maybe 256 proteins that proteins and enzymes are very similar. So it's why I'm using the terms interchangeably. Anyway, 256 of these that are needed for the simplest life. And just trying to get the one at random would take, well, longer than the supposed age of the universe. I've actually heard, and we've talked about this before, Fred Hoyle, British mathematician and astronomer, has suggested there are actually about 2,000 enzymes that are needed for the simplest. He looked at an average single-celled creature. And 2,000 enzymes, he calculated the odds of just randomly, throwing chemicals together, randomly producing all 2,000 of these enzymes. He said the odds are 1 chance in the number 1 with 40,000 zeros after it. Now you remember the number of atoms in the universe is roughly estimated to be about 1 with 80 zeros after it. So it's so far improbable as to be, I think if this isn't impossible, I don't know what is.
It is impossible. You bring that up. I brought some quotes with me. I'm glad you reminded me of Sir Frederick Hoyle. Now, Sir Frederick Hoyle held a position that Stephen Hawking holds now at Cambridge University. It was Isaac Newton held the position first. It was an honorary position because he was like the 10th wonder of the world almost, Newton in his time, greatest mathematician. And Hoyle, with another guy named Wick Ramasinghe, call themselves world-class mathematicians, astronomers. There's very few that have the capabilities of doing the math that they can do.